Determine the convergence of the improper integral and find the value if it converges. Okay, question A, we have 0 to 1, 1 over square root of x dx. This looks like a regular integral, but it is not, because this x is 0, square root of x is 0 when x is 0, and that means the denominator is 0, and thus this entire thing is undefined at x equal to 0. And 0 is indeed in this interval, because it starts at 0. That means, although it looks like a regular integral, you really have to use limits to correctly find out the value. Alright, so let's continue. This would be 0 to 1 of 1 over, rewrite the square root of x as x to the 1/2 power, and then rewrite that as x to the negative 1/2 power, because negative powers means that this thing is in the denominator. And by doing so, I can write this as an x to the nth power form and apply this power rule, which says you have to add 1 to the exponent and put the reciprocal down here. So let's apply that. We add 1. 1 plus negative 1/2 is positive 1/2. Put the 2 over 1 and you put 1, 0. Okay, this is where you have to be careful. You should not plug in 0 right away, because 0 was a point where the denominator was undefined. So you should really think of this as limit of k going to 0 plus of 2 times x to the 1/2, 1 and k. And that means it's when you plug in 1, it's 2 times 1. And when you plug in k, it's 2 times k to the 1/2 power, where k is sent to 0 plus. That's the proper way to do it. Okay. In this case, it does converge to 2, so it looks like you get the same answer regardless of whether you use the limit or not. But you will see in the later examples that we do here that actually you might have a completely different answer when you try the limits. Alright, so we plug in 0 plus. Now what happens? We have 2 minus 2 times 0 to the 1/2 power, but 0 to any power is 0, so that's just 2. So that's the answer to A. What about B? B also has a problem, this time when x is equal to 1. When x is 1, this denominator is 0, and 1 is indeed one of the endpoints, so we actually have to use limits in computing this. Now the antiderivative of 1 over square root of 1 minus x squared, as you know, it's arc sine of x, and instead of saying 0 to 1, we're going to put 0 to k and limit k to 1 minus. See, the idea is to avoid this problematic point. So rather than plugging in 1 right away, we plug in something that's slightly less than 1, so that the interval 0 to 1 minus, this interval here, would not contain the 1 itself. Okay, so if it's like 0 to 1 here, I want the k to be slightly less than 1 so that this interval does not contain 1. If I had k going to 1 plus, that's going to be a problem, because in that case k will be slightly bigger than 1, and then this interval will still contain 1, so that's not a good idea. So we don't do that, we make k going to 1 minus. Alright, so that gives us limit k going to 1 minus arc sine of 1 minus, no, actually there's k minus arc sine of 0. Arc sine of 0 is 0, and arc sine of k is arc sine of 1. So k goes to 1, so you get arc sine of 1, and arc sine of 1, sine becomes 1 at pi over 2, so the value is pi over 2. If you forgot the graph of sine, you should remember that sine graph looks like, here's 2 pi, pi, pi over 2, 3 pi over 2, and the graph looks like this. And indeed, sine becomes 1 at pi over 2. That's why arcsine of 1 must be pi over 2. Now let's move on to question C. C, it has integral 0 to 1 of 1 over 1 minus x squared dx. And we see that the denominator can be factored as 1 minus x and 1 plus x. Now we know that when the denominator can be factored like this, it requires partial fractions to integrate. So let's figure out how it is decomposed into two fractions. So I'm going to write one of them as a over 1 minus x and the other one as b over 1 plus x. Multiply this thing both sides so that the left side just has 1, whereas on the right side I have a times 1 plus x and then b times 1 minus x. Plug in x equal to -1, gives you 1 equals to 2b, so that b is equal to 1/2. Also, plugging in x equal to 1 makes this one 0, and then you have 1 equals to 2a, so a is also 1/2. So that means this integral here is now same as integration of 1/2 over 1 minus x plus 1/2 over 1 plus x dx, integral from 0 to 1. Okay, and these can be integrated using the f prime over f formula. If you integrate f prime over f dx, that's ln of the denominator. So we apply that to, especially to here. If you differentiate 1 plus x, that's 1. So the second part can be written as 1/2 ln of 1 plus x. Let's just write down the absolute value of the denominator, and then everything's fine. And then over here it's slightly different, because if you differentiate 1 minus x, that's -1, and this is like 1/2 times +1. So the trick is to multiply a negative and put a -1 there so that it does become f prime over f. So you end up with -1/2 ln 1 minus x absolute value. Okay, and to this we have to plug in 1 and 0. Okay, maybe I should just divide this part where we did the calculation for the partial fraction decomposition. Alright, once again, the problematic point is 0 is okay. If you plug in 0, there's no problem. This thing becomes 0 when x is either 1 or -1, and -1 is not part of this interval, so we don't care about -1. However, 1 does cause a problem, so instead of putting 1, we better be writing down limit k going to 1 minus, so you're approaching 1 from the left, and then we should be plugging in k accordingly. Okay, and then that gives us limit k going to 1 minus of -1/2 ln k is plugged in. Plus k, and then when you plug in 0, you get ln of 1 and ln of 1, and we know that ln of 1 is 0. So basically we have to figure out what the limit is. This is okay, this is ln of 2, but here when k is sent to 1 minus, you know that 1, you already have a 1 and you're subtracting a 1 minus, which means this is like 0.9999, and you're subtracting from 1, so it's like 0.0001, so it's something that's close to 0 and it should be positive. So at the end of the day, what you're getting is you get negative 1/2 of ln of 0 plus 1/2 ln of 2. And if you recall the graph of log of x, graph of log of x looks like that. So it goes to negative infinity as you go towards to 0. So this actually becomes negative infinity, but times negative 1/2 gives you positive infinity. So positive 1/2, positive infinity, plus something that's still some quantity, finite quantity. So the answer is positive infinity. That's the answer. Maybe I should use a black. So positive infinity, that's the answer. In the fourth question, you have x equals to 1 as the number that makes the denominator undefined. And this time, you see that 1 is inside the interval. It's not one of those endpoints. It's neither 2 or negative 1, but 1 is between negative 1 and 2. In such a case, you have to split the integral into 2, one from negative 1 to 1, and the second one, which is 1 to 2. And if either one of these diverge to infinity, then we have to say that this integral does not exist. So let's track each of these integrals. They both have the form x minus 1 to negative 2 power. I'm writing this way so that we can use the power rule to integrate. Okay, so from 1 to 2, x minus 1, negative 1 dx, whose integral is, by the power rule, if you add 1 to the exponent, that's negative 1, and reciprocal of negative 1 is negative 1, so from negative 1 to 1, plus we have the same integral, it's just different endpoints, so from 1 to 2. And remember, it's this 1 that is causing the problem, so we have to introduce the limit. So let's put a k for each of those 1s. So for the first one, instead of the 1 here, I'm going to put a k. And then for the second one, I'm going to put k for the one down here. Okay, and we're taking k, for the first one we're taking k to be 1 minus because we are approaching from the left of 1. See, negative 1 is left of 1. It's less than 1, so when k is trying to expand the interval to have this interval to be negative 1 to 1, you want k to be going to 1 from the left. That's why you put 1 minus. In the same way, this time you want the k to be approaching from the right. 2 is bigger than 1, so you want to put k as 1 plus in this case. That means limit k going to 1 minus. Let me rewrite this as 1 over x minus 1, because negative 1 part is that. And in there, k is replacing x, so I end up with 1 over k minus 1 minus negative 1 over, this time it's negative 1 minus 1. The second one has k going to 1 plus negative 1 over k minus, this time you have to plug in 2 first. So we plug in 2, and then 2 minus 1, and then minus negative 1 over k minus 1. When you have something slightly less than 1 and subtract 1, that will be close to 0 but slightly less than 0. So In this limit, you're going to get negative 1 over 0 minus. This is negative 2. Negative is positive, but there's another negative, so it's negative 1/2. This is 2 minus 1 is 1, and you get negative 1 for this part. And then you have negative and negative, which is plus. And then here, k is slightly bigger than 1, and if you subtract 1, that will be slightly bigger than 0. So I end up with 0 plus. Now, 1 divided by positive, that's positive. 1 divided by negative, that's negative. And 1 divided by something like 0.0001 will give you something like 1,000. So you know that as x goes, as this number gets closer and closer to 0, in this entire fraction will go to positive infinity. Same thing here, it will be negative infinity, but with this negative, it will be positive infinity too. These two adds up to 3 over 2 plus infinity, so you end up with infinity minus 3 over 2 plus infinity, which is infinity. Now, if you didn't do all this, you'll be fooled into thinking that this integral will give you just negative 3 over 2. And that will give you a totally wrong answer. So you have to be careful. The reason you want to be careful about these improper integrals is sometimes if you just naively calculate, you get an answer that's completely wrong. Next question, E. We have to integrate x e to the x. Let's do this indefinite integral first, because that requires integration by parts, or the tabular integration. So, x differentiates to 1, 1 differentiates to 0, e to the x integrates to e to the x, e to the x integrates to e to the x, plus minus plus. That way it's x times e to the x. This gives you negative e to the x. Last row has to be multiplied and integrated. So you get 0 integration, which gives you c. So adding these, the answer you get is, you get the answer x times e to the x minus e to the x plus c. That's the indefinite integral. Therefore, when you have integral from 0 to infinity of x times e to the x dx, that will be x times e to the x minus e to the x, and you're plugging in 0 and infinity. And because this part is infinity, you have to use the limit k going to infinity of, let's factor the e to the x, so you get x minus 1 e to the x, and then you integrate from 0 until k. If you plug in k, you get k minus 1 e to the k, limit k going to infinity. And then if you plug in 0, that's e to 0 is 1, 0 minus 1 is negative 1, and negative 1 times 1 is negative 1, so you get negative 1. Now, what do you get if you set k to infinity? E to the infinity is infinity. Infinity minus 1 is infinity. So this first part actually gives you infinity times infinity, which is infinity. And even if you have plus 1, that doesn't matter, because the entire thing goes to infinity. So that's how you solve E. Now, F is very similar, so let's try to do that also. Negative infinity to 0, x e to the x dx. Same deal, it's the same integral, except that this time it's negative infinity to 0, so you have to write it as k going to negative infinity of x minus 1 e to the x negative infinity to 0. Okay, which is, well, first when you plug in 0, this is negative 1. And e to the 0th power is 1, so if you plug in 0, you get negative 1. Minus, now you have the one that involves k. So let's put k here. K goes to negative infinity, and x k minus 1 to the e to the k. Well, this time it's harder to do, because if k goes to negative infinity, e to the negative infinity is 0, whereas negative infinity minus 1 is negative infinity. So you really don't know. You basically have infinity times 0 indeterminate. You don't know which is going to be going faster. So we have to use some other methods to determine this. Now, one nice approach would be actually to do the substitution. So just say, instead of using k, say t goes to infinity and put negative t instead of k. And this is good because now you can rewrite e to the negative t as 1 over e to the t, and that becomes a fraction, which means you can apply the L'Hopital's if possible. Okay, once again, to explain what I did, k is now replaced by t, replaced by negative t. Since k is negative of t, if k goes to negative infinity, t would go to positive infinity. And all k is now replaced by negative t. Okay, so furthermore, we have negative 1. Multiply the negative inside, so that I have limit t going to infinity of t plus 1 instead of negative t minus 1. Also, using the fact that negative power is same as the positive power with that brought to the denominator, now we have this, and this now can be seen to be infinity over infinity, which means you can use the L'Hopital, so you end up with negative 1 plus limit of the derivative of top and bottom, which is 1 over e to the t, and now I know that 1 over e to the infinity is 0, so the final answer is negative 1 for this f. Okay, for g, we have 0 to infinity of 1 over 1 plus x squared dx, which is arctan of x 0 to infinity. So you have limit k going to infinity of arctan of x 0 to k, which is arctan of k minus arctan of 0, and you have to take limit k going to 0 infinity. So let me delete this. Okay, it's limit k going to infinity of this. So that means I need to know what arctan of infinity is. And surprisingly, this is not equal to infinity. It's not equal to 0 or 1. It's actually some strange value. Let me explain why. First, think about the graph of y equals to tangent of x. Graph of tangent of x has asymptotes at pi over 2 and also negative pi over 2, and it's shaped like y equals to x cubed, except that y equals to x cubed would extend beyond pi over 2, but this has a vertical asymptote here and there. Also, y equals to x cubed is flat, kind of flat near 0. Y equals to tangent x is more like y equal to x near 0. So they're indeed very different. Okay, so this is the graph that you have. Of course, it's periodic, so this is going to repeat to the right and also to the left. But when you try to define the arctangent of x, you only take the tangent x from negative pi over 2 to pi over 2. And then you use this to define the inverse function, which we call as arctangent of infinity, arctangent of x. Okay, so for example, if I want arctan of 1, what do? We look for the case where the tangent becomes 1, and we ask the question, what is the number that will make this value 1? And the answer is it's pi over 4. So this is pi over 4 because tangent of pi over 4 is 1. Therefore, when you ask arctangent of infinity, that's like you're going up and up and up, and you're looking for the angle where it will produce that infinity. And the answer is, as it goes further up, your angle will get closer and closer to pi over 2. So the arctangent of infinity is pi over 2. Okay. Therefore, arctangent of infinity is pi over 2. And arctangent of 0 is 0 because tangent of 0 is 0. So this says arctangent of 0 is 0. And the final answer is pi over 2. Okay, find the area enclosed by two graphs, y equals to x squared plus x plus 3 and y equals to 2x plus 5. For these, it's important that you know how to draw the graph. We know that this is a parabola opening up, and y equals 2x plus 5 is a line that's slanted this way. So they must be crossing each other like this because only this way you're going to have some enclosed area. So that's the idea. We need to know when they meet. To do that, we have to set them equal to each other. So x squared plus x plus 3 equals to 2x plus 5. Solve this by moving the 2x to the other side. We get negative x, negative 2 equal to 0. So x minus 2, x plus 1 equal to 0. That gives you x equals to 2 and negative 1. So we know that x is negative 1 here, and over here x is 2. That means the area is the integral from negative 1 to 2, in this, from negative 1 to 2, of the top minus bottom. And in this graph you see that the line is above the parabola, so we should put the line first and minus the parabola x squared plus x plus 3. And when you do this, don't forget to use the parenthesis because you're subtracting the entire thing. And that's negative 1 to 2 of 2x minus x is x, 5 minus 3 is 2, and then you still have a x squared. So that's the integral you have to do. Integrate those, you get 1/2 x squared plus 2x minus 1/3 x cubed, and you're plugging in 2 and negative 1, which means, so when you plug in 2, 2 squared is 4, 4 divided by 2 is 2. 2 times 2 will be 4. When you plug in 2, 2 to the third power is 8. Minus, when you plug in negative 1, negative 1 squared is positive 1, so you have positive 1/2. Negative 1 times 2 is negative 2. Negative 1 cubed is negative 1, but there's a minus here, so it is positive 1/3. And then let's add the integers first. 2 plus 4, negative negative 2, so that's plus 2. 2 plus 4 plus 2 gives you 8. And then I see a 1/3 and another 1/3, so let's add these two together. Because of this minus, it's really negative 8/3 minus 1/3, so it's negative 9/3. And then we still have this 1/2, so that should also be there. And 9 over 3 is just 3, so we have 8 minus 3, which is 5, 5 minus 1/2. And since 5 is 10 over 2, if you subtract 1/2 from it, you get 9 over 2 as the area enclosed between the two. Find the area between the graphs of y equal to x plus 2 and y equals to negative x squared minus x plus 10 over the interval 1 to 3. Also sketch the region. Okay. Let's sketch the region. Well, let's first figure out when they meet. X plus 2, negative x squared minus x plus 10. Move everything to the left side. You have x squared. Negative x becomes positive x, so x plus x gives you 2x. plus 10 becomes negative 10, so we get negative 8. 2 minus 10 is negative 8. And this factors as x plus 4 and x minus 2, which gives you that x equals to 2 and negative 4 are the two places where they meet. Now, we know that 2 is between 1 to 3, but negative 4 is not. So only 2 is going to be relevant for our discussion here. Let's try to draw the graph. I know that this is like an upside down parabola, and I also know that this is kind of like a slanted line. It should be slanted this way because it's positive slope. And it must be that this is negative 4 and that's 2. But we're only thinking about between 1 to 3 here, so the region must be something like this. Okay. It says sketch the region, so we probably need to do a little better than this. So let's just plot some values, plug in some values, and we're going to work with it. So we know that 2, 4, when you plug in 2, you get 2, 4. 2, 4 is a common point. It's a point where they intersect. And at 1, if you plug in 1 here, you get 8. So here's 8. And then when you plug in 3, 3 squared is negative 9 minus 3, negative 12 plus 10. So negative 2 is what you get at 3. So at 3, we have this. So the parabola will be like this. You're going to have a parabola. I'm not so sure how it looks over here, but definitely it's like that. Okay. On the other hand, the straight line, we're passing through this, and I know that the slope is 1, and slope 1 is like 45 degrees that way. So that's the graph. And over the interval 1 to 3, you end up with the graph that's like here. So it's basically the same thing, but I just added more coordinates by plugging in the values because the question said to sketch the region. Okay, when you sketch the region, you realize that there's something happening before and after 2, because before 2, the parabola is over the line. After 2, the parabola is below the line. That means when you calculate the area, you have to do top minus bottom, and the role of top and bottom changes. And that's what you have to consider when you're solving this question. So area is, you have to integrate from 1 to 3, but from 1 to 2, you have to do the parabola minus the line, whereas from 2 to 3, you have to do line minus the parabola. Okay, that is going to be equal to integral from 1 to 2 of negative x squared minus x is negative 2x, and then plus 8 dx plus from 2 to 3. It's basically the same thing, just negative of what we have here, because if you put a negative of this, this becomes positive, that becomes negative. So we're just going to write down positive x squared plus 2x minus 8. Or you can simplify this. You're going to see that it's exactly the same thing. Now we integrate by using the power rule. 1/3 x cubed minus x squared plus 8x. That's the integral of the first one, and we have to plug in 2 and 1. Whereas the second one, it's the same thing except the opposite sign. Alright, so we have, when you plug in 2, it's 2 to the third power, which is 8, 8 over 3, minus 4, plus 8 times 2, which is 16, minus, when you plug in 1, it's negative 1/3 minus 1 plus 8 plus, this time when you plug in 3 cubed is 27, but 27 divided by 3, this will give you 9. When you put 3 squared, that will also be 9, minus when you put 3 times 8 is 24. Minus, and you have to plug in 2, so it's 8 over 3 plus 2 squared, which is 4, and minus 16. And we have to add these numbers together, and we'll just consider the fractions first. So you have negative 8 over 3 plus 1/3, so it's negative 7 over 3 minus 8 over 3, which is negative 15 over 3. That's what we get if we just add the fractions. Negative 4 plus 16 is plus 12. Negative 1 plus 8 is 7, but there's a minus. 9 plus 9 is 18, minus 24, it's negative 6. And then over here, that's negative 12, but there's a minus here, so it'll be another positive 12. So there'll be 11 total, but you have a negative 5, so it's negative 5 plus 11, which gives you 6. Now, question C, we need to sketch the area, sketch the region enclosed by x equals to negative y squared plus 1 and x equals to negative 3. Now, when you have y squared as equal to x, either you have a parabola opening right or left. This one is this case because there's a minus in front, so it's this one. So this graph, x equals to negative y squared plus 1, will be a graph that looks like this. It's a parabola opening left. And x equals to negative 3, x equals to negative 3 is like a vertical line passing through negative 3. And it better be crossing this way. If the vertical line was here, then there's no enclosed area, so it must be crossing in this way. So this is what we are trying to find. To find this area, so this is x equals to negative 3. To find this, we first need to figure out when they meet. In order to find the intersection, we have to set them equal to each other. Since x is this, and x is also equal to negative 3, we should set negative y squared plus 1 equals to negative 3, so that when you move y squared over to this side and negative 3 to that side, we have 4 equals to y squared. That gives you y equals to plus or minus 2. So now we know the 2 points. The coordinates are negative 3 comma negative 2 for this one, and this point will be negative 3 comma positive 2. We know that the x coordinate is negative 3 because this vertical line is x equal to negative 3. Okay, now we have to find the area, but this time it's easier to do the integral not by using cross-sections, vertical cross-sections. Instead, you want to take horizontal cross-sections, because if you take horizontal cross-sections, this means you're slicing this. So area is the sum of small bits of area, and these areas will be like very thin horizontal slices whose thickness will be extended in the y direction. So we're trying to integrate by y, and its length would be the difference between the x coordinates, and because x coordinate of this is always negative 3 and x coordinate of this is given by this function, we have to do negative y squared plus 1 minus negative 3 to do the integral, where y goes from negative 2 to positive 2. Okay, so the integral is from negative 2 to positive 2. Negative 3 is positive 3, so negative y squared plus 4. And we integrate, which gives you negative 1/3 y cubed plus 4y. And you plug in 2 and negative 2. Oh, I wish I used the evenness of this function to just integrate from 0 to 2 and double it. That would have been easier. So what would you get? You get, when you plug in 2, that's 8 over 3. 8. So 8 minus 8 over 3 will give you 16 over 3. And when you plug in negative 2, you're going to get another negative 16 over 3, which gives you 32 over 3 as the answer. Okay, find the limit of this sequence where you're sending n to infinity. This is exactly same as limit of regular limit that we've been doing. The only time that the limit of sequence may be different from limit of functions when you have x is when you have a sequence that has negative 1 to the nth power. In this case, this just makes the numbers alternate between plus and minus. If this is included in, say, something like this, then this makes it alternate. So that's the only time it might be slightly different from doing limits of a sequence and limit of a function. But these are all just the same. So we solve it just like how we solved L'Hopital's. This is like infinity over infinity kind. So we apply the L'Hopital, differentiate the top, which is 4n. Differentiate the bottom. Well, we'll use the product rule. Differentiate this, you get 5. And then plus, differentiate the second one, which is 2. So that's the limit. And this is still infinity over infinity type. So we differentiate the top again, differentiate the bottom again. This time you just differentiate this because that's a constant multiple. So differentiating, you get 5 times 2, which is 10. And this one also gives you 5 times 2. That's another one. And that just gives you a number. So it's 4 over 20, which is 1 out of 5. Okay, here, this one, it's hard to figure out what kind of limit this is, because if you plug in n going to infinity, 3 to the infinity minus 4 to the infinity, that doesn't look like, it's infinity minus infinity, so we don't know whether it's going to be negative infinity or positive infinity. So we have to do something else, and that something else is to divide both top and bottom by 4 to the nth power. So let's do this. n going to infinity, 3 to the n minus 4 to the n divided by 4 to the n. Also 3 to the n plus 4 to the n, and you divide this by 4 to the n. 3 to the n over 4 to the n is 3 over 4 to the nth power, and 4 to the n divided by 4 to the n is 1. Down here is 3 over 4 to the nth power. 4 to the n divided by 4 to the n is plus 1, limit n going to infinity. And if you have 0.75, which is 3 over 4 is 0.75, you have something less than 1 and you multiply by itself over and over and again, what's going to happen? It becomes 0, right? So you end up with a 0 minus 1 over 0 plus 1, which is negative 1. So this is a question where you don't use L'Hopital because you can't say whether it's 0 over 0 or infinity over infinity. Now this last question, that's something that we've been doing for L'Hopital's. It's an exponential form, so we raise it over e, write it as e to the ln of something. But the better way is to first say t equals to 3 over n. Do this transformation so that n would be 3 over t. If you multiply by n and divide by t, you've solved for n, and n is 3 over t. Also, you know that as n goes to infinity, t goes to 3 over infinity, which is 0 plus. So these are the things that we use in order to change this into a limit t going to 0 plus 1 plus t. And instead of n, if I put 3 over t there, I end up with 6 over t. Okay, we now use the trick that we've been using for all these exponential forms, which is to write any number as e to the ln of a. So we write this as e to the ln of 1 plus t to the 6 over t. And then this hops over the log, which is e to the 6 over t ln 1 plus t, limit t going to 0 plus. And then now this is infinity over infinity, which means it's this can be thought as infinity over infinity, which means you can use the L'Hopital. So we differentiate 6 log of 1 plus t, which is 6 over 1 plus t. And the denominator, if you differentiate t, it's 1. And therefore, when you send t to 0 plus, this will be 1 plus 0, so you end up with e to the 6th power. So that's the limit of part C. Explain why the following series diverges. Okay, this test for divergence says if a summation, for summation to converge, limit of an as n goes to infinity must equal to 0. Now this doesn't mean that if the limit of an goes to 0 as n is sent to infinity, the summation will converge. It doesn't say that. It's like the minimum condition, okay? But to actually converge, it will have to meet more stringent criteria. That's what we're going to see later. Okay, so let's see. We have this summation. We have to see that limit of n goes to infinity of this sequence, whether this does go to 0. Well, it doesn't, because 4 over 3, since 4 over 3 is bigger than 1, 4 over 3 into the infinity will be just multiplying something that's bigger than 1 over and over again, so that's going to be infinity. So this is infinity, therefore, thus, sigma n from 1 through infinity, 4 times 4 over 3, the sum of these things will also go to infinity. If you add, if you have something that's getting bigger and bigger and bigger, and you're adding them, the summation will also be infinity, because you're adding something that's getting bigger and bigger and bigger. Now let's try to work on the second one. For this one, 3 plus n over 5 plus 2n. We take the limit of the sequence, and since n and 2n are the dominant terms, you end up with a limit of n over 2n. And n cancels, so you get 1/2 as the limit. What does this mean? This summation, 1 through infinity, of 3 plus n, 5 plus 2n. This summation means you're plugging in 1, so when you plug in 1, it's 4 over 7, and then when you plug in 2, that's 5 over 9, and then 6 over 11, and so on and so on. You're adding these things, but at some point you realize that the things that you're adding is somewhat close to 1/2. Now what happens if you add 1/2 over and over again? It will grow without any bound, right? So this will again be infinity. That's why this will diverge. Actually, in the exam, all you have to write is just this, and say by the test for divergence, sigma n from 1 through infinity, 3 plus n over 5 plus 2n diverges. That's all you have to say. But I just provided here some intuitive reasoning why that would be so. Okay, for part C, we have summation of n from 1 through infinity of -1 to the n. What's that? When n is 1, it's -1, and then when n is 2, it's +1 plus -1 plus 1 plus -1. So what's happening here? This is excuse me. This is when you add this much, you get 0, but when you add this much, you get -1. When you add this much, it's 0 again. When you add this much, it's -1. So the summation just alternates between 0 and -1. It never gets closer and closer to a single value. So this will be another example of a series which diverges. But again, that's just an intuitive explanation. To just prove that this series diverges, all you have to say is that the sequence inside the series, see, this sequence is being added. So when you add sequences, that's called a series. You're adding -1 over -1 to the nth over and over again. So that's the sequence that you're playing with. If you send this to infinity, this does not exist because it alternates between, well, when n is even, it gives you 1, and when n is odd, it gives you -1, so 1 and -1. It never becomes a single value, it just alternates between the two values. And then say, thus, by test for divergence, the series sigma n from 1 through infinity of -1 to the n diverges. That's the proper way to explain it. Okay, use the integral test to determine if the series converges or diverges. Now you're adding 1 over n times log of n cubed, and the integral test says that if you do this integral, you replace this sequence by x, so x ln of x cubed, and then dx, and instead of 2 to infinity, instead of adding 2 to infinity, if you just integrate 2 to infinity, if this converges, then we know that this series converges. If this integral diverges, then we know that this sequence, this series diverges. That's the statement of the integral test. So when it says use the integral test, what you have to do is you devise an integral, an infinite integral similar to that series, and we have to determine whether this is convergent or divergent. The difference between these two is that here we don't have any good means to actually calculate the sum. No such formula exists, but over here we know how to do the integrals, so we may or may not get definite answer here, and we can use that to determine what will be the answer to A. Okay, so we'll try to integrate this. And for this one, it's an integral where ln of x is involved, and we learned that when ln of x is involved, often the strategy is to make t equals to ln of x, so that when you raise both sides over e and ln cancels, and that gives you e to the t equals to x. And then if you differentiate, well, actually it's easier to differentiate here. If you differentiate e to the t, it's e to the t, so e to the t dt is dx. Okay, using this we can compute the indefinite integral. Let's worry about the definite integral later. We'll just play with the indefinite integral. So this x is now replaced by e to the t, and log of x is replaced by t, And then we have integral of e to the t dt. Okay, that's good. Yeah. So integral is e to the t dt, and now you have e to the t canceling each other, and you just have integral of 1 over t cubed, which is the integral of t to the negative 3 dt, and that means you can use the power rule, which says you add 1, put the reciprocal, this reciprocal of this is 1 over 2 with the minus, plus c. But then since t is the substitution, we have to bring it back to x as log of x, so at the end of the day you get 1 over 2. T squared should be here, but since t is log of x, we have log of x squared plus c. Okay. Now what does that mean for this integral? Therefore this integral 2 to infinity of 1 over x times ln of x cubed dx is limit of k going to infinity. Remember, this is a improper integral, so you need to involve k there. Negative 1 over 2 ln of x squared, and because this is a definite integral, you don't put c there. We just use this much and put 2 until k. Which means when you put k there, it's negative 1 over 2 ln of k squared, and then minus of minus, so that's plus 1 over 2 ln of 2 squared with k sent to infinity. Now what's ln of infinity? When k going to infinity is plugged here, log of infinity is infinity. Infinity squared is infinity, so you have 1 over infinity. So what that gives us is just 0 from the first one. And that means we just have this value, which is a finite value. Since this is 0, we just have this one. And because this converges, we know that sigma n from 2 to infinity of 1 over n times log of n cubed converges. By integral test. By integral test. Integral test. And it's basically the same idea. So let's try the second one. This one we write down from 1 through infinity, replace x n by x. So we have x over square root of x squared plus 1 dx. And this one again requires u substitution. Set u equal to, you can say u is equal to, you could set u as x squared plus 1, but if you do u equals to square root of x squared plus 1, this will actually lead to a simpler result. Here's another trick. Instead of differentiating like this, square both sides, so you get u squared equal to x squared plus 1, and then differentiate this. So u squared differentiates to 2u, so you put 2u du. X squared differentiates to 2x, and 1 differentiates to 0, so you end up with 2x dx. And we solve this for dx, so you get dx equal to 2u over 2x du, which is u over x du. Okay, why is this good? Well, if we look at the indefinite integral, we have x over, we decide to call this thing as u, right? So it's u times dx is u over x du, so you put u over x du, and they just cancel, which leads to 1 du, which is u plus c, but because u is square root of x squared plus 1, we end up with this as our indefinite integral, and that makes this calculation very easy now. This integral is therefore limit k going to infinity of square root of x squared plus 1 And then you have to put k and 1 there. So limit k going to infinity of square root of k squared plus 1 minus, when you plug in 1, that's square root of 2. And this is infinity, and square root of infinity is infinity, so you have infinity minus square root of 2, which is infinity. And since this diverges, we know that sigma n equals to 1 through infinity of n over square root of n squared plus 1 diverges by integral test. Okay, last one. You now have to integrate square root of n plus 1 in the denominator. I should put x here. Dx, you integrate 1 through infinity. Well, this integral is quite trivial. I'll just give you the answer here. So you can check that this is indeed the antiderivative of this, or to get this you should write that as a negative 1/2 power and integrate this using the power rule. That's how you get to this. And then I put k going to infinity, and then that gives you limit k going to infinity of 2 square root of k plus 1 minus 2 square root of 2. And again, this is infinity minus 2 radical 2, which is infinity. And that means sigma n going n from 1 through infinity of 1 over square root of n plus 1, this diverges. Now this last part C is an interesting example, because if you look at it, 1 over square root of n plus 1 as n is sent to infinity, this is 1 over infinity, which is a 0. So you're adding things that are getting smaller and smaller, almost nothing, yet this summation still manages to diverge to infinity. So this actually becomes infinity. So this is again a counterexample to the idea that, oh, maybe any sequence that goes to 0, if you add them, it's going to converge. Actually, it's not that simple. There are cases where sequences go to 0, whereas the summation still goes to infinity. The most famous of these examples is the sum of 1 over n. When n goes from 1 through infinity, this goes to infinity. But there are many other examples like this one.